This is a talk that was intended to be given yesterday. Unfortunately, there was a miscommunication so that all the emails we had said 2 p.m. and unfortunately the announcement said 10 a.m. So this is happening. I'm going to give this talk day after as if there's an audience for the purpose of recording it. First, I want to say thank you to Raphael for an invitation to give this talk, and particularly for giving me a focus, the Reeh-Schlieder Theorem. I'm going to begin by showing you how I think about quantum mechanics and quantum field theory as if they're data set and signal analysis formalisms, but in particular, not paying any attention to the stories that are told about particles and particle properties. Then within that way of thinking about quantum mechanics and quantum field theory, I'll take a first look at quantum field theory, at the Reeh-Schlieder Theorem, and how renormalization suggests an axiomatic nonlinearity for the Wightman axioms in particular. Finally, I'll show you how the Reeh-Schlieder theorem justifies that nonlinearity, not merely suggests it. Finally, in the last five slides, I'll show you something about quantum gravity and how this kind of thinking can be applied to that. So if we have an experiment, we want to know something about this central region. We surround it by many devices, each of which is connected by a signal line to a piece of hardware that analyzes that signal in real time. So when the signal suddenly changes from a low value to a higher value, we look up the time of the event and store that in computer memory. Then at some later time, days or weeks later perhaps, we analyze that data, write a paper, and so on. Now, there's a particular moment here that happens only once from an engineering perspective, and that is the point at which the electromagnetic field in the signal lines here is converted to a digital format so that we can store it, so we can examine it and store it subsequently. That doesn't tell us anything about what's inside these devices directly, but of course we can know something about what happens inside those devices directly because we have centuries of experience, and indeed we've characterized this particular device before we install it into the experiment, and so we can say what kinds of electromagnetic activity and other activity there would be within each of these devices. So what I'm saying here is that from an experiment we obtain data sets. Those contain just lists of numbers, and from that we can compute relative frequencies and other statistics straightforwardly. So something, in any theory we're going to use seriously, should generate expected relative frequencies so we can compare those with the actual relative frequencies from future data sets. Anything more than that doesn't give us better empirical confirmation. Nonetheless, generating the same expected relative frequencies in different ways does give us different intuitions, and so that's not something to be discounted. Now, one example of an intuition is the idea of systems and particle properties. But in the first instance, we just have that measurements give us data sets, and it's only through long chains sometimes of inference that we can say that a particular entry in the data set is caused by a particular particle and its particular properties. So even though particle properties can be intuitively important, nonetheless they can also be misleading. And so particle properties are not obvious enough that we should take them to belong in a set of axioms. And indeed, quantum field theory is lukewarm about particles, much warmer about field theory, of course. And from a different direction, we have machine learning also suggests a focus on data sets, not on the causes of the entries in the data sets in the first instance. Now, as well as having no place for particles and particle properties, axiomatic quantum field theory also has no place for tensor products and partial traces, which are fundamental for the definition of entanglement for particle properties. So we can't introduce entanglement directly either. Nonetheless, the idea of entanglement, the idea of particle properties is something that is often useful, and not saying we can't have it, it's just that we should hesitate before using it and be very careful about how we use it, because it's not something that is always obvious. So now I want to focus on data sets, and it's particularly helpful, I think, to work within an algebraic quantum mechanics instead of the usual sort of quantum mechanics, which begins with a Hilbert space corresponding to a system and its properties being associated with operators. In this case, we will instead take this algebraic formalism, which you find in the literature, though not with this focus. The eigenvalues of a linear operator, so these diagonal entries here, should correspond to the data values in a data set, so the D1, D2, taken to be down the diagonal of a matrix. So with this kind of approach, there are abstract measurements, M1, M2, M3, we can add them, we can multiply them. We have that a data set and its data values correspond to a linear operator and its eigenvalues. And if we were thinking out in terms of classical probability, that would correspond as well to a random variable and its outcomes in a sample space. If the algebra is non-commutative, we would say it's quantum. If the algebra is commutative, we'd say it's classical, but otherwise exactly the same. And we have these four properties as well, which we'll assume because we do want to make contact with quantum mechanics. So now that gives us abstract measurements, but it doesn't tell us anything about expected dataset averages. And so we introduce a state rho that tells us what the expected dataset average will be for a particular measurement, so we can compare it with the actual results when we do collect data. So we have that a state applied to a measurement operator is just a sum of probabilities times the different eigenvalues, and for the nth moment we have this construction just the same. Now I'm going to use generating operators quite a bit through this talk, and so I'm going to introduce a generating operator, an exponential generating operator, and I'm going to use an imaginary, which I'm going to introduce specifically this purpose, and I'm going to call it J, and indeed following sort of the engineer's perspective, because we're going to take the inverse Fourier transform of that to give us, in an engineer's sort of mathematics, a direct distribution. And that gives us, with the state, a characteristic function that generates all the moments of the measurement M1. And we can take the inverse Fourier transform of the characteristic function to give us a probability distribution. So this now is the notation in this formalism for a probability distribution. Now, there are four properties that a state is taken to satisfy in all of the literature, which is conditioned on the properties one has for relative frequencies, which are required to be positive, normalized, and real valued. And correspondingly, we have these three algebraic equations. And as well, because we can add relative frequencies, we have what I call von nonlinearity, because we have, even if A and B do not commute, nonetheless, we require that this should be satisfied. Now, the reason we have that specification of a state is because with it, we can also use measurement operators to modulate the state rho. Because this construction here, with an operator and its adjoint bracketed around a measurement operator and normalized, also satisfies the rules for it to be a state. And so that gives us many, many states if we have many operators, and that's the basis of the Gelfand-Naimauck-Siegel construction of a Hilbert space. So whereas we started off with a structure that did not have Hilbert spaces, so seemed rather remote perhaps from quantum mechanics, now we do have a Hilbert space, so it's a bit closer. Nonetheless, we're talking about data values, not about properties of systems. So there is that difference remains. Now we have as well that the GNS construction very usefully lets us think of a state applied to a measurement operator as a vector and its covector bracketed around a measurement operator, and similarly for a modulated state. So how does this look for quantum field theory? If you look in at quantum field theory textbooks in the first few chapters, you'll find a decomposition of a scalar field into lowering and raising operators, and indeed in a Fourier sort of construction. Now, it's an operator value distribution. It's not a measurement operator, but we construct what I will call an F measurement and use this notation for it by smearing with a test function, as it's called in the literature, an operator value distribution to give us that. F of x is called a test function, but it's also called a smearing function in other parts of the literature. And if you look in the signal analysis literature, you'll find it's called something very similar, is called a window function. Because indeed, f of x tells us where and how big and what shape the f measurement is. Now, this construction is linear, so we can write the f measurement as two components, a lowering and a raising operator, where the complex conjugate here is a consequence, one can say, of this minus sign here. Now, for quantum mechanics on the previous slide, we had measurement operators, M1, M2, M3, and so on. But to make contact with the experiment, we also need a list of descriptions to go with each of those measurement operators. Now we have two lists, and we can merge those into a single structure by taking the descriptions to be an index set for the measurement operators instead of using 1 through n. And we do that because that's precisely what we do when we use quantum field theory in the kind of approach I'm suggesting. And that is, the F measurement gives us many measurement operators, where the functions now are formal idealized descriptions of how measurements are not point-like on space-time, on Minkowski space. So in this kind of construction, quantum field theory is pretty much the same as algebraic quantum mechanics, except that for each measurement, it adds an idealized description of what that measurement does. So this is really much closer to algebraic quantum mechanics than the usual sorts of construction, which assume there's such a thing as systems and particle properties. So now, given this presentation of the free quantized Klein-Gordon field into lowering and raising operators, we want to know what the commutator is between those two things, and indeed it is just a pre and a product of two test functions f and g. Given that, and these four equations, all we need to know is that those four equations plus some background knowledge about algebras, of course. But with that, we can use a Baker-Campbell-Hausdorff identity to construct for this expression, using the F measurement generating operator, a Gaussian expression. And if the test function is real valued, we can take the inverse Fourier transform of that to obtain a normal probability distribution with the variance given by the pre-inner product of F with itself. Now we can introduce modulated states as well by using a G measurement and its adjoint bracketed around this operator that gives us a modulation of the probability distribution. It also gives us a Hilbert space that is smaller than the full Fock space, which requires us to introduce all possible functions on space-time that are reasonably well behaved. Now, indeed, quantum optics is a field theory that does use only a few different window functions, but is a field theory nonetheless. Now, all of that has been entirely about local operators. Everything is placed in space and time in a local sort of way, but we can also introduce the vacuum projection operator, which is non-local in the sense that it doesn't commute with any of the F measurements. Nonetheless, we use it routinely, and indeed it allows us to construct projection operators, many of them, which is indeed used whenever we use an S matrix, for example. So I find it very helpful to think of the vacuum state of a quantum field as a broadband, noisy carrier signal. And it's broadband because any wave number that's on the forward mass shell does contribute to the carrier signal. It's noisy because we have no information about the relative phases of each of those contributions. Because it's noisy, we have to talk about probabilistic modulations of measurement results. We can't fix measurement results precisely as we might if we're doing classical mechanics. So we saw on the previous slide that we obtain a normal distribution for an F measurement. We can displace that by using a unitary operator, a unitary G measurement operator, bracketed around an F measurement generating operator. That gives us this probability distribution, which is simply a displacement of the vacuum state by an amount that depends on the pre-inner product of F and G. So if F and G are very close to each other, then there's likely to be a larger displacement. If they're very far apart, then the displacement will be small or indeed zero. We can also, however, do something considerably more because we can use the G measurement itself and its adjoint bracketed around the F measurement generating operator to construct this probability distribution wherever the overlap of F and G is at its maximum. On the other hand, if F and G are very far away from each other, then this modulation will be very small. It will be mostly look just the same as the normal distribution. So this expression here, the pre-inner product, determines the geometric structure of a free quantum field pretty much completely. It tells us what stochastic transmissions the carrier signal supports. If we try to impose a modulation on the vacuum that isn't in the forward mass shell, for the case of the Klein-Gordon field, then there will be no transmission of that. So this fixes something, a dynamical property of the vacuum state. And it also tells us how a modulation changes measurement results everywhere else, in other words. Now, we can also modulate joint measurements, and that's what we do when we engineer coincident events in many devices, which is obviously something we do very often when we're doing quantum computing. And we want to describe that. And so we can describe that by using what I'm going to call a Wigner characteristic function for many measurement operators. And it's only, I call it that because it's only if these F measurements all commute with each other that the inverse Fourier transform of this will give us a probability distribution. So the Wigner characteristic function I wanted to introduce because it gives us an effective presentation of the algebraic structure. We have that this expression we can expand using the Baker-Campbell-Hausdorff identity into a noise factor and a non-commutativity factor. and that becomes a Gaussian noise term and a non-commutativity term, just those two parts to this construction. Then that fixes the algebraic structure. We also want to fix the geometric and dynamical structure, and we can do that in multiple ways. So for the Klein-Gordon field, we have the pre-inner product is given as a projection to the forward mass shell, and then we take the product of the wave number components. For quantum optics, we have something similar, but obviously different. We project to the forward light cone, and then we construct two space-like 4 vectors, both of which are orthogonal to the wave number. And because of that, this is negative definite construction, given the metric I've chosen. And so this is a pre-inner product. Both of these are positive frequency because of the theta k 0, and they're both manifestly Lorentzian translation invariant, which is necessary for us to consider this to be a quantum field theory. But this doesn't give us a representation space of the Poincare group. However, we can, if we want that, introduce an inductive limit over all of Schwartz space, and that gives us the Gaussian Fock space for all possible test functions that are well enough to behave for the particular condition. So, as a prelude to the Reeh-Schlieder theorem, point out that for a classical Klein-Gordon field, we commonly talk in terms of the retarded propagator, which is a distribution valued solution of a classical inhomogeneous Klein-Gordon equation. And because it's inhomogeneous, this equation, we can have 0 in the backward light cone and at space-like separation, but in the forward light cone, we can have a non-trivial propagator. In contrast, if we consider the quantized Klein-Gordon field, we find that the 2-point vacuum expectation value is a distribution value solution of the classical homogeneous Klein-Gordon equation. Consequently, the backward light cone and that space-like separation are non-trivial. What I think this means is that if we want to change our model of an experiment, we can't just introduce the experiment and just have done with it. That's all we need to do. We have to arrange for the parts to exist in the past and for those parts to come together somehow to give us the experimental apparatus. So because we have to change what happens in the past, that also changes what happens as space-like separation, because this is a time-like separation from this. In other words, for this kind of model, there's no deus ex machina. We can't just do what we like. We have to do what we like. We can only do what we like if what we like corresponds to what the Klein-Gordon equation agrees with, so to speak. So this 2-point vacuum expectation value fixes the geometry of the quantized Klein-Gordon field completely. And if the geometry is complicated, it's because of these properties. So the Reeh-Schlieder theorem for the mathematics, I'm going to send you away to the literature. The mathematics literature is quite extensive on this. The Reeh-Schlieder theorem asserts that for a free Wightman field, which I'll show you in a few slides' time, local operators acting on the vacuum vector can approximate any vector that's constructed using operators that are far away. And that's a consequence of the analytic structure of this kind of model. In other words, of the properties I've just shown you in the previous slide for the particular case for a free field. That approximation is in the sense of the Hilbert space norm. So for all vectors, which we can construct by applying an operator to the vacuum vector that is of finite norm, then there are operators which have support only in some small region for which this norm expression is arbitrarily small. The vacuum vector, however, is an extra special case in a dense set of special cases that for almost all vectors in the Hilbert space, such approximations do not exist. And indeed, in general, we really can't approximate an arbitrary operator X using an operator that is contained in some small region. In the operator norm, we would generally have that this difference between X and A would not be approximately 0. So we can't perform remote measurements. We can, in some sense, construct remote state preparations, but we can't perform remote measurements. Now, as a prelude to interacting fields, for a Gaussian field, the Wigner characteristic function fixes the algebraic structure as we saw. This is, in fact, a generating functional form of what are called the Wightman functions. So that for any Wightman field, we can use the Wightman reconstruction theorem to construct a Hilbert space. And that's just a specific version, which includes things like Lorentz invariance of the more general GNS construction. Now, Lagrangian deformations are not well defined in 1 plus 3 dimensions, not well enough defined for a mathematical purist, at least. So we want alternative ways to deform the free field case. What we want is some expression that is a deformation of this and yet is still a state. And that is what I'll start to talk about now. So the Wightman axioms, to me, look extremely straightforward, and it seems remarkable that there are no known, well-defined interacting models in 1 plus 3 dimensions, even after over 60 years of considerable effort. So it seems to me reasonable to ask how we can weaken the Wightman axioms. We might want to introduce something completely different, but that's not what we're going to talk about today. So we have a Hilbert space that supports the unitary action of the Poincare group. There's a vacuum vector that is invariant under the Poincare group, under that Poincare grouping action. Quantum fields are measurement operator value distributions. So they're linear maps into the star algebra of measurements. Measurements also support an action of the Poincare group, in this case an adjoint action. Microcausality just says that there will be commutativity at space-like separation. Completeness is just that the action of these F measurements on the vacuum vector generates all of the Hilbert space. There are no extra vectors, so to speak. The time slice axiom I'll talk about in a little while. Crucial to point out, I think, there are two linearities implicit in the Wightman axioms. States are linear. We have von Neumann linearity, and we need that absolutely to ensure that there is a probability interpretation. And I don't want to give that up at all. On the other hand, the F measurements are axiomatically linear in the test functions because of the way we constructed them using operator value distributions, and hence we have this linearity as well. So I'm going to argue on the next 5 slides that renormalization and a few other issues suggest strongly that we should allow quantum fields to be nonlinear maps into this algebra of measurements. I'm going to start off relatively slowly by just talking about signal analysis, where if we were talking about f of x and g of x as window or modulation functions, we think of them as an impulse and a response and a pairing of those two things, then the pre-inner product we would think of as a resonance between those two things. And of course, as a first approximation, we might well think that a linear structure for that is appropriate. But we would always know as engineers that we would need to introduce something that was a nonlinear resonance farther down the road. So I think it's just the case that linearity of the field is just not so obvious that it should be axiomatic. We can use and should use the Wightman axioms in 2 different forms, one in the linear form and one in the nonlinear form, and see how those constructions differ. Now, if we worked with a more general construction, not associated with the Wightman axioms at all, we might have text descriptions as indices for our measurement operators, in which case there's no definition of linearity for that kind of description. There'd be no reason to insist on linearity. All we would need to construct a Gaussian model for probability theory's purpose is to have a matrix for each pairing of one description with another, and that matrix has to be positive semi-definite. And that's a structure known to mathematicians and to computer scientists as a kernel. Now, I don't think this is a strong argument, but we can find a stronger argument, I think, when we look at real space renormalization in particular, where if we suppose that a test function is a smearing function on this square region, and we split that into 9 fragments, then we apply majority rule, which simply says we measure in each of these 9 regions this measurement operator. We decide whether the result is positive or negative. We add those all together, and then we decide whether the result of that addition is positive or negative. Then this fragmented F measurement, as I'm going to call it, we can iterate that construction over and over and over again. This fragmented F measurement is clearly nonlinear in f of x, and that's different from the inaccessible bare F measurement, as we might call it, precisely because the F measurement is linear in the test function. But this dressed fragmented F measurement is arguably still a quantum field. It's the sort of thing we would certainly use if we were doing effective field theory. So I think that's a slightly better argument that we should allow and expect F measurements to be nonlinear in the test function. Now, we can also find support when we think about the renormalization group in a way that's suggested, to me at least, by a book by Hollywood in 2013. And he suggests that a measurement F is just a function of interaction parameters, of some characteristic length scale that tells us about the experiment, about the measurement, and also a choice of cutoff, either mu or mu prime. And the content of renormalization is just that whether we choose mu or mu prime, the prediction from these two different theories should give us the same measurement results, statistics, and so on. But clearly, for anyone who's at all detail-oriented, L is unacceptably vague. If we want more detail, then the natural place to go to is the test functions that we might want to use to describe a measurement and indeed experiments. And so instead of L, we write some set of test functions, f1 through fn. And indeed, I think it's appropriate to think of these test functions as a complete description of an experimental apparatus. So if we were entering them into design software in 2080, we would hope for it to be able to predict experimental results just as engineering software already does for bridges and so on. Now, the cutoff scale appropriate for an experiment also depends on details of the experiment. So it should also be a functional of the same test functions. Indeed, that fixes an effective dynamics as well. And so we can absorb all the dependence on those test functions into a single Euclid structure, which simply says this boldface f is a functional of these test functions. That's clearly more nonlinear than what we started with. Renormalization for different cutoff scale functional simply becomes the more or less trivial statement that f must equal f prime. That's a more complicated argument, but the end result is just the same. We should allow ourselves to use the Wightman axioms in a linear form or a nonlinear form according to how complicated we're willing to be. Now, if an f plus g measurement is not equal to an f measurement plus a g measurement, then we can think of this difference of those as a measurement of how much what is measured by an f measurement interacts with what is measured by a g measurement. And because this is about interactions, it's also related to measures of entanglement between those two different measurement results. And I won't go into that in detail because that would be a whole new talk. This, I suggest, is a measurement and modulation holism. Its measurement is not the same as the sum of its parts. But I don't think this is any more acceptable or unacceptable than the idea of what is measured holism, which is the usual way we think about these things. Neither should be excluded axiomatically. We should allow ourselves to consider both the Wightman axioms, linear and nonlinear versions. Now, one can find intimations towards this kind of construction in the philosophy of physics literature, which I won't go into because of time. If we also have that if an f measurement is nonlinear in those test functions, we can use functional derivatives of that structure to give us a two-point vacuum expectation, two-point operator value distribution, for example. Now that is something that's very clearly not in the Wightman axioms. It's very clearly something very much different. You can actually find in the literature, Wayne Polizu and collaborators of his have used this kind of structure to model bound states, as one might reasonably think it would be useful for. But point out that if an f measurement is not expressible as a functional Taylor series, however, if, for example, we use a cutoff version of the test function f as a smearing function, then that has singular points in many places on the imaginary axis, and that will result in the possibility of topological structure if it's topologically non-trivial. This is something that clearly needs much more to be said and much more mathematics done than I'm saying here. One can also find in the literature on the Wilsonian renormalization group flows that there's an intubation again towards invariant distributions, just as we have here. But I suggest that, given the reasoning on previous slides, we should just use nonlinearity, and given that that also gives us the possibility of topological structure. I'm not going to go through this anymore because of time. So I've argued that renormalization suggests nonlinearity. I'm going to argue now that nonlinearity is in fact enough. We have, for a conventional Lagrangian deformation, we apply that to a free Wightman field. In some later chapter of an elementary textbook, you'll find an expression something like this, which we can write in this sort of way. And this is just a generating functional using J as now still as a test function, but it's not well defined if it's Lorentz invariant, in which case this vector is not in the Hilbert space. But if we can find a regularization for which the vector this vector is of finite norm, then we can apply the Reeh-Schlieder theorem. so that we can use local operators acting on the vacuum vector which approximate that. So we can use a structure such as this, something that's constructed using only nonlinear local functionals of the test function J. Now, effective field theories and renormalization make that more complicated because they introduce mass and length rescaling, but we can accommodate that by just using fields of different masses for different functionals. So instead, for each functional as a index by kappa, we have also an operator value distribution index by kappa as well to accommodate rescaling. Now, we know very well that the physics can be approximated by a regularized field theory. And indeed, we can hope that we could eventually construct a really well-defined renormalized version of that, and yet we haven't managed to do so yet. Nonetheless, we can also approximate this structure we've just seen by a local and nonlinear sort of construction, dependent again on mu, which gives us a completely different geometrical sort of picture. Because if we compute the 4-point vacuum expectation value that comes out of, that is generated by this or this, that gives us sums of loop integrals. So we have a structure, this particular Feynman loop diagram would have 10 integrals in which y1 through y10 are all integrated over all of space and time, very much a global structure. On the other hand, if we take functional derivatives of this, if we take a functional derivative of this, we can obtain a 4-point vacuum expectation value, and that will give us expressions such as the functional F1 applied to F1 and the functional F1 applied to F3, and that will go into a particular overlap, which is just pairwise. And so we'll have many of those pairwise relationships, resonances or overlaps between those fragments. We'll have many products of those things as well, and many of them together. So this is an inverse problem. We want to find local, nonlinear fragment functionals and measurement operators that locally approximate what happens in the bulk for path integrals, and that all works because of the Reeh-Schlieder theorem. Now, the interplay here between local and global is similar to what we have for holography, because this all depends on the analytic structure of the Wightman axioms. And so if you are comfortable with holography, you perhaps ought to be also comfortable with this kind of construction. So I've argued that analysis of renormalization and of path integrals suggests we should introduce local nonlinearity, and that it's enough. On the other hand, so as a consequence, we want to express this as some manifestly Poincare invariant functional of the lambda I and Fi's. And we can decompose that in any way we like. Any way we would decompose any functional, or we might want to construct it in some other way. We want to do so in a way that gives us good intuitions about different experiments. And so for some experiments, we might want a different kind of construction. But I don't want to prejudge what better mathematicians than I am might do. They might want to use a mathematics much more elaborate than the Wigner characteristic function that I've taken to be a useful proxy for the structure of an interacting quantum field theory. Now, if we're thinking in engineering and data analysis terms, I suggest the axioms should look rather different from what we're used to from the Wightman axioms. We should start with some finite set of measurement operators that are nonlinear in the test functions on Minkowski space. And then if we have many test functions, that will be a larger algebra than the algebra we'll get if we have just a small number of test functions. We require only that there be a manifestly Poincare invariant state, which gives us the possibility of using the GNS construction of a vacuum vector and of a Hilbert space. Then if we want to work with a representation space for the Poincare group, we can do so by introducing an inductive limit. We also require some kind of spectrum condition and microcausality so that this commutation relation is trivial if the F and G are causally separated. Now, if we look at the test function space, it really is the case that engineering and physics applications mostly don't care about representations of the Poincare group. It's only when you have mathematicians that would be desirable or indeed even necessary to prove many things, of course. But in quantum optics, we do typically use just a small number of test functions. suggest an axiomatic approach should not exclude a standard engineering practice. Manifest Poincare invariance can be enough, and we shouldn't insist on a representation space. Now, the time slice axiom is somewhat similar in that if we know all expected measurement results on a Cauchy surface here, that determines all expected measurement results in this causal diamond. For engineering and physics, we know much, much less than that. And indeed, suppose we have some set of measurements for which we know the experimental results, and we know as well the relationships between those measurement results and some new measurement. Then we want a state just to give us conditional probabilities for a measurement that we're going to perform in the future. That's as much as we can expect, or indeed could want. It just gives us a probability distribution. Now, this construction, I point out, is naturally multi-scale, all scales, and it's neutral about reductionism because these test functions, f1 through fn, could be very small test functions that tell us something about a much larger new measurement, but it could be the opposite way around. We could have all of these could be very large and tell us something about something that happens at extremely small scales. All of those can be independently of large or small scale or of any scale. So I'm going to show you two tentative constructions. I don't pretend that these are how physics is, but this kind of construction is a first step towards a more elaborate sort of constructions, perhaps. We can construct a nonlinear Gaussian field for which this two-measurement vacuum expectation is nonlinear by taking the usual sort of construction, which is linear, and then adding to it a similar sort of structure in which we have a nonlinear functional, which is local, acting on f and on g, and then we take the pre-inner product of that nonlinear structure. That also allows us to construct a Hilbert space and all of the trimmings that go with that. And that's going to give us a sum of many nonlinear binary representation relationships instead of a sum over paths. So I think of this as an impulse response model with a stochastic transmission in between, but also it's multi-channel. Each of these pre-inner products corresponds to a different channel and different kinds of impulse and response, all mishmashed together. So now we can construct as well. In a slightly different construction, we have a recursive cloud of measurement operator fragments can emerge. So this actually takes inspiration from an integral presentation of the phi-4 theory, where instead of integration over all points in space and time, instead we do integration over just a discrete or continuous set of values of kappa, indexing different functionals. And so for a test function f, we will construct many fragments within it, and then fragments within that, and so on. So that gives us a quasi-fractal kind of version of this kind of construction we have above. So I think this gives us the possibility for many more models because these axioms, as we now have them, are weaker than the Wightman axioms, so there must be more models. We have nonlinearity as well as dispersion and noise, and because we have multiple kernels, there are possibilities now for interference between those different kernels. So we can hope for models for things we haven't been able to model, for tables and chairs, hands, and indeed for things like thermodynamic transitions in physics generally. And if it's not enough to weaken it this much, then we should obviously look at weakening them some more or introducing completely different axioms. So how does this work play out for quantum gravity? If we're given some measurements that have different descriptions, description 1 through n, all we need for us to be able to construct a Gaussian state is just a matrix, a kernel indeed, for each pairing of those descriptions that is positive semi-definite. If we, on the other hand, have managed to do that and do much more, we've managed to construct a successful deformed optics, which combines many kernels indexed by kappa in such a way that this construction is still a state, and it's successful. It's empirically very validated as quite good. Now for quantum gravity, we can introduce just a new description, which has a bivector test function, as we have for quantum optics, plus some description of a background we want to impose. Just because we want to impose it doesn't mean that the vacuum will accept that modulation. Nonetheless, we say what we want, and it tells us whether we can have it. Wherever a kernel indexed by kappa occurs in our successful deformed optics, we simply replace it by a pre-inner product that in the DIs instead of that, the same kappa. And that gives us a candidate optics and quantum gravity. It's not the first one we think of is not going to be the right one, obviously, but it gives us a starting point for other constructions. Now, I suggest this gives us a measurement and dataset theoretic approach to gravity. This isn't about quantizing gravity, about gravitizing quantum or gravitons, nor is it about any particular structure at very, very small scales. So we have, adapting what we had before, in an engineering sort of approach, we have tentative axiom set for quantum gravity. So we have measurement operators are nonlinear in those measurement descriptions. We want there to be a manifestly diffeomorphism in invariant state, allowing us to construct a Hilbert space. Then we have as well that quantum gravity requires there to be a spectrum condition and microcausality, but that's a non-trivial sort of thing to do when the geometry is non-trivial. Causal structure being as multifaceted as it is in a non-trivial geometry, that's going to be hard to work with. So I suggest instead we might think in terms of a quantum non-demolition gravity, which I will show you in a few moments what I mean by this, which takes quantum non-demolition measurement as its basis instead of the ordinary sort of quantum measurements. So we have what I will call an FQND measurement, which are universally compatible. This is terminology from quantum computing. It just means commutativity. But we can use the vacuum projection operator to construct a non-commutative algebra that allows us to do anything we can do with quantum gravity, as I'll show you in a while. Now, the advantage of this is it makes h bar only about the amplitude of what begins as just a Poincare invariant noise. It's not also about measurement incompatibility. Now, you recall that there were two terms, each of which involves Planck's constant. We have the Gaussian noise term, but also a non-commutativity term. And this is a reprise of slide number 9. But if we talk about signal analysis, negative frequencies in that context are not associated with negative energy. So they're not associated with instability, backward causality, or anything really unreasonable. It was just a matter of whether we're talking about the real signal. So we work with something like the cosine of omega t, which is obviously both positive and negative frequencies, or whether we are working with the analytic signal, which is only positive frequency. This is effectively the quantum mechanical case, and this is the signal analysis real signal case. So it's natural in signal analysis to remove the theta k0 here and here. And doing that zeroes out this non-commutativity term perfectly. Gives us an everywhere commutative, noisy, classical random field theory with, however, a Lorentzian translation invariant h-bar scale noise. H-bar is the amplitude of this noise, completely different from the kt that one has as the amplitude of thermal noise, and thermal noise is also not Lorentz invariant. So this is a different version, but it's still a classical sort of model because everything is commutative in the first instance. Now, I can show you what this looks like for quantum optics in particular. So we have these 4 equations, as before, giving us this non-trivial commutation relation. But for quantum optics, we can find an involution, a bullet involution, as I'll call it, for which this equation is satisfied. And because that equation is satisfied, we can construct an FQND measurement in which this complex conjugate and the bullet involution are in the opposite order than they occur if we consider the F bullet measurement that we were using before. And because of that difference, we find that the FQND measurement all commute with each other, no matter where they are in space and time-like separation or not. So these FQND measurements generate an effectively classical quantum non-demolition optics field. It's a commutative algebra, but the Hilbert space we're working with is exactly the same as we had before. We have the same vacuum vector and exactly the same raising and lowering operators. So this is a classical kind of construction that exists entirely within quantum optics, and we can use it or not as we like. Now, I can show you one particular example of a bullet involution, which is not unique, however, by projecting two positive and negative holistic components using the Hodge dual here and changing the sign of one of those two components. Now, this bullet involution is Lorentz invariant, but it's not translation invariant, nor is it local. However, both quantum optics and quantum non-demolition QND optics are Lorentz invariant and translation invariant when considered separately. It's only the relationship between them that is not translation invariant. So now, some random thoughts on quantum gravity. I'm really not so far along in discussion of quantum gravity to be able to say, and here is something very, very solid. point out that we know nothing about the vacuum state until we measure it. We only learn something about its causal structure when we modulate the vacuum in different ways that we can't do them all at the same time. And then we measure the different consequences. And that's extremely close to the sorts of arguments one sees when we discuss causal modeling in the classical causal literature. I also point out that invariance, now we're talking about large language models much more than we were 5 years ago, for example. Those we should think of as being about much more than diffeomorphisms. If we have a text and video about an experiment, about a measurement that is in Chinese or in English or German, it should make no difference to the predictions that come out of our experiment or out of our theory. Those might be extracted automatically from a journal article and its supplementary information. There's another aspect here that is that if we have a conversation over coffee with someone who's done an experiment very similar to what we want to do before, then that can be crucial to whether or not our experiment works or not. If they give us a hint that allows us to construct the experiment and make it work properly as we want it to, then that is useful information that a large language model can encode, whereas it would be quite difficult to encode that kind of information into a formal test function sort of formalism. Now, I point out as well that the coordinate systems we use for measurement descriptions, I think they should be continuous. It doesn't matter whether the real world is discrete or random fractal, continuous, loops, strings, whatever it may be, because once we have two measurements that I know about and you know about, we both know what the description is in some particular coordinate system, I can say to you, well, let's do 0.4, some mixture of those two things, something in between those two things. And I say, well, 0.4 is where I want it to be. And you can say, I know what that means. I can do that experiment. We have a conceptual and coordinate system within which I can say to you, do this experiment like this and see what happens. And it can be done. So coordinate systems can be quite different, and continuity is helpful because even if the world is discrete or random fractal, we can nonetheless have a continuous description of the measurements. Now, this first part here is simply a summary of the first 3 slides. It's something that I talked about in considerably more detail in a talk in May 2025. And for a summary of what I've said here, however, I've argued that an analysis of renormalization shows it is a surreptitious nonlinearity, and that it suggests strongly we should introduce nonlinearity into the Wightman axioms. The Reeh-Schlieder theorem shows that introducing nonlinearity is enough to match the empirical success of perturbative QFT. The problem with all that is that the introduction that I've shown you today is non-constructive. I can't, for a particular Hamiltonian, say to you, this is how you present that same physical state, that same physical experiment in this new formalism. Nonetheless, I think it is helpful that we can construct a more empiricist quantum gravity or quantum field theory by focusing on measurement description instead of focusing on what is measured. It's a dual sort of formalism in that respect. It gives us a more rigorous way to construct interacting field theories and quantum gravities, taking everything to be about data sets and signal analysis formalisms. Now, you may be very upset that this is not realist enough, but quantum non-demolition field theory, I suggest, can be pretty much as classical as you like because it is just a commutative algebra. I don't advise that. I think we should be sophisticated about how we work with measurement. Nonetheless, that is a possible way to think about these things.